We have seen that the convergence of the Newton-Raphson method is faster than that of the bisection method, meaning that we can get sufficiently close to the root with fewer iterations. However, the faster convergence comes at a cost. Let's note that in each iteration, the bisection method only requires testing the sign of the midpoint f, while for the Newton-Raphson, we have to evaluate both f and f prime at the current xk. And this is not to mention you also need to find the derivative of f, which can also be inconvenient. So to circumvent evaluating f prime of x directly, interpolation methods instead of Taylor series approximation may be used to approximate the function f. The idea is that we can fit a line or a polynomial curve with the last few iterations x and fx. For example, the second method uses a straight line through the x and fx from the last iteration and that from the current iteration to approximate f. And then instead of finding the 0 point of the original function f, we find where the straight line intersects with the x-axis. In other words, where that straight line is equal to 0. Here's a graphical illustration for the second method. Suppose that we are currently at iteration 1 and we have x1 and fx1, as well as that from the last iteration, which is x0 and fx0. We fit a straight line through these 2 points, and at some point the straight line will intersect with the x-axis. And this is going to be our next x2. The convergence rate of the second method is somewhere between the bisection and the Newton-Raphson method, and that's around 1.618. It should be no surprise to you that higher degree polynomial interpolation may further increase the accuracy in approximating the function f, and as a result, increase the convergence rate. However, computing the root of polynomial isn't always trivial. There may not be a unique root, and there are cases where the analytic root may not exist. This is where the inverse quadratic interpolation method can be used as an alternative. The idea is as follows. So originally, maybe we are trying to fit a polynomial interpolation across a few points of x and f-axis. And then we will see where that polynomial intersects with the x-axis. In other words, we need to find the root of that polynomial, and that's going to be hard. But the inverse quadratic interpolation method flips this around. Note that for a one-to-one function, h of x equals 0 implies h inverse of 0 is equal to x. Since we're fitting a polynomial interpolation anyways, why don't we flip the x and y? So instead of fitting a quadratic polynomial h of fx case given the x case and finding the root of this polynomial, we will instead fit a quadratic polynomial of the x case given the fx case, so the other way around, and evaluate it at 0. Here is a graphical illustration of the idea of inverse quadratic interpolation. Let's suppose that this is the function we're trying to find the root for, and these are the 3 points of x's and the f function evaluated at these values in the last 3 iterations. Regular quadratic polynomial will use x, that's equal to the original x-axis, and y, that's the fa, fb, and fc's. And then the polynomial will look something like this. For the inverse quadratic polynomial, our x's will be the fa, fb, and fc's, and our y's will be the a, b, and c's. So if we fit an inverse quadratic polynomial, it will look something like this. And then this polynomial will intersect with the x-axis at some point. And this is the point where we set the y equal to 0. So by setting y equals to 0, we'll be able to find this point. So h inverse of 0. And this intersection point is going to be our next guess for the x value or the root. The Brent method is a hybrid of bisection with inverse quadratic interpolation to find the root of a nonlinear function fx. Specifically, given a current interval a to b containing the solution, in other words, fa and fb have opposite signs, and also let's assume that fb is the current best guess. In other words, the absolute value of b is less than or equal to that of a's. Absolute value of fb is less than or equal to that of fa. So in other words, the fb is closer to 0. Let's also assume that c and fc are the guesses and the corresponding function evaluated at the guess from the previous iteration. Then using the AFA, so FA and A, FB and B, and FC and C, these 3 points, an inverse quadratic polynomial will be fitted. So you might be thinking about how we can fit this. This is not something we will go into details over here. And if you're interested in the formula, you can look at the book. But for example, you can use a Lagrange interpolation polynomial where the formula is right there and you can use it conveniently. And then if the 0 point of this inverse quadratic polynomial is outside the interval from a to b, it means that the gas is too far away. Then we will use bisection method instead. However, if the 0 point of the polynomial is within this interval from a to b, then we will update the interval with the 0 point that's in this interval. We're not going to write the algorithm ourselves, so the R function uniroot actually applies this method. So let's see an example. Let's solve the previous equation, the quadratic equation. And this time we're going to use the uniroot function inside R, which employs the Brent's method. This function requires specifying a few things. The first is the function for which we want to find the root for, so f in this case. And we'll also need to specify a starting bracket. So that is a bracket where the solution is inside, that captures the solution. So like before for bisection, we will use the bracket from 0 to 5n. So the code is actually quite simple. We just call the uniroot function, specify the f, which we already created, a and n values, and then we specify the lower bound of the bracket is 0, and the upper bound is 5 times n. And I will return you a few objects, including the root, the f function evaluated at the root, and the number of iterations. As you can see, this time it took 14 iterations, and it also got us to a x value that is around 4.18 or 4.19. And the resulting f function evaluated at this root is also really close to 0. So while the uniroot or the Brent's method is a little bit converges a little bit less as fast compared to the Newton-Raphson, it has the safeguard of the bisection method, and at the same time, it doesn't require us to calculate and evaluate the derivative. Before we move on to talk about optimization, let's also introduce a very crude method for root finding, and this is known as grid search. So you can imagine if I tell you, let's play a game of guessing a number between 0 and 100. Well, one thing you can do is to guess each of them and see when I said that's the correct answer. And that's the idea of grid search. And the idea is quite simple. So suppose we have an interval from a to b that contains the solution. then we're going to first find equally spaced values x1, x2, all the way up to xn inside the interval from a to b. We will evaluate the f function at each of these x's. And then we will pick the x such that fx is closest to 0 as the approximate solution. So here's the code for doing this for our earlier quadratic root finding problem. We will create a sequence of x values from 0 to 100, and there are a total of 10,000 of them. So each of them increments about 0.01. We will evaluate the function f at each of these x values, and then the root will be the x such that the absolute value of fx is the smallest, in other words, closest to 0. And that gives us something around 4.19. You can see this method is not very efficient. It requires us to evaluate the function f at a large number of possible x values. And the solution also isn't as good as what we have obtained using the other methods.